course. As you can see, many people disappeared. But yeah, the advanced one. Okay, so what are you going to learn the advanced one? And the other question is like, what are the prerequisites? Like, so what's the difficulty of the course? So I think I wrote a short little blurb about the difficulty of the subject. If you don't understand stuff, you'll probably be on a third year level. However, if you know, like if you're a second year-ish, like if you're a first year that you understand some sort of math, so if you did 4 unit, it should be fine. If you're just a first year, if you did 4 unit, and if you have some little programming skill, you should be fine. If you're a second year, you should be fine.
So do you need no specific programming, or you just meant like general programming skills?
So I would say just kind of, so if you have some sort of maths formula, can you actually type it into the computer? Something like that. Right, so we're not going to like do, well we are going to do some complicated stuff, but it's important. And if you're third year, well, you know, it should be fine. But yeah, so today I was going to teach you guys about the introduction of simulations. So we're going to learn something about simulations. So that's today's topic. I was actually going to go into programming stuff, but I decided probably simulations is a more interesting thing. So okay. Whatever. Oh yeah, it's going on. Okay. Okay, so simulations. What do I mean by simulations? So a simulation is just you're trying to, so remember I told you that supervised, so machine learning is you have data, right, and you want to make some model, right? However, so we're going to focus mainly on statistical algorithms, and what we do is we want to create some sort of theoretical model, then we get data, and then we kind of change the model. So that's kind of like the opposite way around. However, these are still extremely important. So if you're pretending to have some sort of virus spreading in an environment, in fact, if you use other methods like machine learning, predicting virus movement is extremely complicated. Weather prediction, for example, is based on a theoretical model, then you have data to optimize your system. So that's the difference. So with simulations, you can do weather prediction, disease prediction, and other types of simulations. So I'm going to start on a basic simulation, for example. So pretend I have some sort of person. Okay, so you know in airports you have like the travelator thing, like you go like the person is over here, and you can just move across, right? So that's like in an airport. I don't know what it's actually called. I think it's travelator. But when you're in the airport, like you use like you just move across. You don't actually have to walk. So the question is, how am I going to model this person moving from here to here? Right, so how am I going to model this? So that's actually the question. So that's a simulation. So how are we going to translate this this scenario into mathematical format? Right, so then so I'll introduce you to you probably understand. So has anyone heard of Markov models? Markov Systems? Yeah, cool. So if you don't know Markov Systems, don't worry, I'm going to explain it. But a Markov model is so you had some old data, like one period before, like 1 second before, and you want to predict the future, like just 1 second after. So that's like Markov model. I'll show you an example. So pretend this is point A, right? So that's the starting point. This is point B, C, D, E, F, G, right? You can put any points as you like. If you go to the quantum scale, you can just do, the right? But anyways, we're gonna focus on discrete systems. So we're gonna chop areas into chunks, right? So these are the chunks. If you're in a continuous system, then these chunks will converge to some sort of line, right? So some continuous area. We're not gonna do that. Okay, that's a bit more complicated. But if you have some sort of discrete system like this, I chop it into chunks, right? So now I'll ask you a question. At time 1, I'm over here, right? So at time 2, so this is time 2, 3, 4, 5, 6, 7. At time 2, what is the probability of moving from point A to point B? 100%, okay? So the probability of moving from A to B is 100%, right? So, correct. 50. Why is it 50?
No, 100.
No, well, it depends, right? There's actually some number, but let's just say it's 100, right? So A to B is 100. So I'll put a 1, right? So now the person is over here, right? At time step 2, what is the probability of moving from A to B? It's still 100. So the person's in B, but the probability of moving from A to B is still 100. Because if there was a new person, they will still move from A to B. That's why it's 100, right? But then now we say, okay, what's the probability of moving from B to C? Then it's also 100, right? So as you can see, A to B is 100, B to C is 100, C to D is 100, and so on. Right, so if you draw some sort of system as a Markov system, so if you treat these as states, A, B, C, D, E, F, and G, right, every single second, the probability of moving from A to B is 100, the probability of moving from B to C is 100, 100, right, and so on, right? And so the probability of moving from B to A, so backwards, is 0, right? And so on. Everything else is 0. You can't move backwards, and you can't skip, right? You can't like suddenly move from here to here, unless that the person walks, right, faster. But we're not going to consider that. We're just going to consider the simple system that the probability of moving from point A to B is 1, right? Every single one is 1, right? So do you guys understand that part? Kind of? No? Yes? No? Yes? No? Okay. So if I want to explain.
First state the assumption you have, then so assumption is it's moving and it can't move backward.
Yeah, correct.
So
you can't move backwards.
That's just one case it can just move to the next one.
Yeah.
So its constraints are there that it can move
Forward.
and for one timestamp it will move one step forward. That's
Correct.
So 100%.
Correct. So the constraint, yes, you're correct. So the constraint is you have to move forward, and you're not allowed to like walk. Like you're not allowed to walk on the travelator. You just have to stay there, and then the travelator's move. That's the constraint. Well, if you do consider like someone walking, right, and if you do consider someone like a child walking backwards, for example, right. Once you gather data, you can see these probabilities. So that's the difference. But anyways, now I have this system. Now my question is, pretend if someone's over here, right? After 5 seconds, where's the person going to be? Is it A, B, C, D, or E? Or F, or G? Right, after 5 seconds. So 1, 2, 3, 4, 5, right? The person's going to be over here. Right, so after 5 seconds, if you use our conditions, right? Now another question, how about after 8 seconds? Where the hell is the person going to be? Probably here. Right, but we did not consider that. So I'm just going to put something else, like outside of the area, right? I'm just going to put Y. Right, so that's why I consider, so now we consider that. Everything else, so the person right now is not on the travelator anymore, so the person can move wherever they like. So I'm not going to consider that. Right, so as you can see, you can ask these questions like, after how many seconds, where the hell is the person going to be? So now, I want to tabulate this in a mathematical format. Right, so I'm actually going to reduce the number. That's a bit more, I'll just put out. Right, so now I'm going to use some sort of table, probability table. Right, so this is a probability table. The size determines how many, like the size, so this is 3, size 3. is just how many states you have. So 1, 2, 3, and the out. So you add one more. Right, and each of these boxes represents your probability. So then I'll show you. So A, B, C, and out. So outside, A, B, C, and out. Right. So question 1. What is the probability of moving from A to A? 0. A to B? 1 and 0, 0. So 0, 0, 1, 0, 0, 0, 0, 0, 0. Oh, yeah, 0, 0, 0, 0. I think that's right, is it? Yeah, okay. So as you can see, there's a diagonal line of 1s. Right? So the probability of moving from B to A is 0, and so on, right? So you filled out this matrix. Right? And this is called the transition matrix. Right? And this matrix converts this like intuition-based system into a mathematical format. Right? And so these are your probabilities. So as you can see, all the rows must add to 1, right? Because all the rows is 100%, right? So the sum is 1, right? Because moving from A to A plus moving from A to B plus moving from A to C plus moving from A to out has to equal to 100%, right? You can't have negative numbers also, right? No such thing as negative probabilities. So you can't have negative numbers. So everything has to be positive. Right, so this is your transition matrix. So do you guys understand this part at least? Like, yeah.
The last one should be 1.
Yeah. Because the out.
Because the next state is not defined, so we will.
Oh yeah, my bad. You're correct. Sorry. Yeah, I'm actually violating the conditions as well. Like it has to. You're correct because the out will always stay in the out. You're absolutely correct. Sorry. Yeah, good. Mentioning my mistakes. But yes, that's correct. So they remember when someone's outside of the travelator, right, they'll always stay outside. So that's why outside, going to outside is always 100%.
But it's not true. Because if you're on the other end, if you're entering the system.
Correct. We're not going to consider that. However, if you have data, that's when I say if you have data, you can work out these numbers. For example, if you see that most people move from A to B at some sort of speed and blah, then these numbers will change, right? Some sort of child will probably move backwards. Some sort of like person will probably not like try to move backwards a little and so stay at A and so on. So these numbers will change. So you're right, if someone goes back to the system, well you actually have to have data to show that. So currently we're just considering someone go on the travelator forever, will never come back. So yeah, so in machine learning, for example, you don't actually have this intuition-based system. You actually have to work this out. The machine will have to work out, oh, okay, so the approximate probability of moving from A to B is this, and so on, right? But you actually, in machine learning, you don't have this table. So in statistical methods, so this is stochastic modeling, we actually have some sort of this system. So we have intuition, then we build a model, then we have data to observe the probabilities. So anyway, so yes, do people understand this table? Kind of? No, yes? Okay, cool. So now the question, remember I asked the question? What is the probability, so after 5 seconds, where is the person going to be? Right, so obviously, well, here, right? 5 seconds. But now, once we have this table, we can actually work that out. So I'll show you how. So, okay, step 1 is, remember I called this the transition matrix? I'm just going to call this T. Okay, T for transition matrix. Okay, so the transition matrix, right, if you write it in matrix formation, right, matrix notation. So a matrix in maths is just a table of numbers, that's all. Right, so if you just matrix notation, so 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, no. 0, 0, yeah, 1, 1, no, wait, did I go right? Oh, no, wait, no, yeah, no, it's here. My bad. Yeah, it's like that. Sorry, yeah. So that's a transition matrix, right? 0, 1, so it's just a translation of this table into, remove all those like table columns and row lines and stuff and just put it into this format, right? So this is a matrix in maths. So now we have the system in a mathematical format, right? So now let's ask a question. So the question was, so let's say that I draw the system again, right? A, B, and C, right? This is outside, right? And let's say that the person starts from A, right? So now we want to populate something called the population matrix, right? So the population, or the vector, population vector, right? The population vector is how much of the person is in A, B, and C, right? So if I do some sort of vector, right? So how much of the person is in outside? 0, C, 0, B, 0, and A is 100%, right? Or there can be any number you like, but I'll just put a 1. Right, so this is you're trying to like work out, oh, this person's 1 over here, right? So that's your system, right? So that's your population vector. Yes, do people understand that? So this is at time 0, right? So this is time 0. Time 1, time 2, time 3, although currently it's just time 0. Right, so at time 0, person A, the person is 100% in A. Yeah? Okay, cool. Now, using this population vector, I want to work out at time 2, or time 1, where the hell is the person going to be? So obviously it's in B, right? But how do we actually express this using this maths? Right, so so do people know matrix multiplication? So in fact, the population at time 2 or time so time just to time 2 is equal to, right, the transition matrix times the population matrix at time 1. Right, so if you so remember this is the population vector 0, 0, 0, 1. Oh, I have to switch it around. Okay, so A, B, C, and out. Right, so 1, 0, 0, 0.
I think it's a transport.
Oh, wait, no. Yes, this is the problem. You have to go the other way around. Yeah. Yeah, sometimes if you can do row-wise or column-wise, but you have to switch it around sometimes, unfortunately, sorry. Yeah, something like this should be fine now. I think that's fine. I always get confused. Yeah, I think, yeah. Right, so if you matrix multiply this, so this is P, this is your population matrix at time 1. This is your transition matrix, right? So you just want to times the population matrix times by T. Right, so if you just do your matrix multiplication, should I do it? So, I don't know if I want to do it. But, I think I got that right. I think so. Normally I just plug it into the computer and check which way is the correct way. If I accidentally do it the wrong way, I just switch it around. But yeah, sometimes but sometimes, it depends on which way you write it. Sometimes it might be like this, but that's because your transition matrix, your columns add to 1. So if your rows add to 1, which is this way, then it's something like this. Okay, but anyways, when you times it across, it should look like this. 0, 1, 0, 0. Right? Just plug it into the computer or like some online maths thing. But when you matrix multiply, your answer will be this. I think. But this should be correct, right? So so now the person is 0 at A, but 100% in B. Right, so now the question is, what happens if I times it the second time? Right, so now the person's over here. If I times it the second time, the person should be over here. Right, and this should be correct. Right, and if the person now is over here, if I times it across again, the person is over here. Right, and then the last step is if the person's over here, if I times it across, it will always be in outside. Right, and if you keep timesing across, it will always be outside. Yeah? Do people get that? So this is just matrix properties. You have to times it across. When you keep timesing, the system will evolve. But then as you can see, As you can see, what I'm doing is I keep timesing. So time 2 is population 1 times the transition matrix, right? So at population 3, so times 3 is just the original the population matrix times the transition matrix, right? So at time, oh yeah, and I was gonna do all right? So as you can see, we can see some sort of pattern, right? So yeah, Pn is equal to the population P minus n times the transition matrix, right? So at any time n or t, right, it's just the original time minus the 1, so the backwards time step, times the transition matrix. Yes, do people get that? Right, this is just applying, like you keep timesing on, right? If the person was over here, right, then it will be 1, 0, right? And if you times this by the transition matrix, you should get this, right? This is when you times the transition matrix. Yeah, do people get that? Kind of? No? Yes? Okay, so right now if you have questions, please ask. I don't actually know if I'm explaining this properly, but yeah, so this is your, so if you keep timesing this, so if you keep timesing the original population, if you keep timesing it on, the system will change. Right, but as you can see, there's some sort of repeating here. Right, look, P2 is the same, right? So why can't we just replace this with P1 times the transition matrix times the transition matrix? Right, because that's the definition of P2, right? And the definition of P3, which is over here, I just replace it with P1 times by T times by T times by T. Right, you're just putting this over here. And then the original, right? You're just putting the T over here, and then bring this all across, down. So P1 times T times T times T times T. Right, as you can see, it's repeating, right? This is just T to the power of 4. Right, this is just T to the power of 3. T to the power of 2, and T to the power of 1. So as you can see, in fact, the population at time T is equal to the original population at time 1 times the transition matrix to the power of T. Right, at any power T, you can work out any single population, right? And that's, right? So we just derived, like, this is your, yeah, do people get that? Like, if you keep times in the transition matrix, you get some sort of, you get so, T minus 1? No, it's just T. T minus 1, so this one's 1, right? Oh, you're right. Okay, sorry. Yes, you're right. Good. Point mistakes, please. Yep, sorry. Yeah, population 2 and then 1. Yeah, I got these silly mistakes. But yes, you're right. It's minus 1. So obviously, like, if you start at time 0, right, then what's that? What the hell is population at negative 1? But yeah, just a reminder, you can't do negative time, right? You can't go backwards in time. So that's just a warning, right? Time has to be at least, right, 0 for this one. This one has to be 0. There has to be 1. Just a warning, right? You can't go, well, you technically can go backwards in time, but I'm not going to do this. Okay, so now we have derived some sort of formula for any time, right? For any single time, the population at time t is equal to the transition. Was it transition? No, is the population at time 0 or 1, right? So the original time times the transition matrix at some sort of to the power of t minus 1, right? So that's your formula for the system. Evolving for any single time, right? So time can be 1, 2, 3, infinity, right? So any single time, this system should work, right? So we kind of model the system of someone moving on a travelator, right? So now I have another question now. Then I have 2 people on the travelator, right? So obviously you know that this person will move over here after time 1, and this person will move over here, right? So now my question is, does this system capture this behavior? Because I only did 1 person. Can I do n people? Right? Can I do like pretend there was 2 people over here? Like some child and mother, right? So that now so it's 2, 1, 0, 0. Right? And this is like some Yeah, so like, can this system model this behavior? And the answer is yes, right? If you plug this as the population matrix P, right, so I reverse it around, so P is 2100, right? If this is the, oh no. Right, if you plug this population into this formula, you will get that at time